Good afternoon, I am Mr. Ish. Thank you for joining me for this video. This chemistry video where we are looking at types of intermolecular forces. An interesting subject because you're looking at the force of attraction between different molecules and compounds, not the forces that exist within the same molecule or compound. There are three types of these intermolecular forces. From weakest to strongest, you have dispersion forces, which are also called London forces. You have dipole-dipole interactions, and you have hydrogen bonding. Most of us are already familiar with hydrogen bonding, but these two are relatively confusing. The dispersion force is the weakest, and it is just the transient or instantaneous fluctuation in electron charge distribution. What does that mean? This means those molecules or compounds which have temporary dipole moments. The key word here is temporary. When you're looking at dipole to dipole interactions, these are found in polar molecules versus the dispersion forces. In this, you have some sort of a bond between a polar and a non-polar, or less polar and a more polar atom. It leads you to have a permanent dipole moment. With regards to these two, they're relatively weak, but this right here is much stronger. These are hydrogen bonds. The type of bonds which are found in those compounds and molecules where hydrogen is directly bonded to this very electronegative atom, oxygen or nitrogen or fluorine. If you were to look at dispersion forces, think about helium atom. You have a helium, and you know helium has an atomic number of 2. Think about 2 helium atoms. Let there be 2 electrons which tend to be on this side and 2 electrons which tend to be on this side. When you compare these two helium atoms, because you have 2 electrons over here, you have a relative negative side over here, you have a relative positive side here. With regards to this, at some particular point in time, you have 2 electrons here, you have a relatively negative side here and a relatively positive side here. These two sides will tend to clump together because you have a minus and a positive. Opposite sides attract. Here you end up seeing, for a very temporary or instantaneous period of time, you end up seeing a sort of interaction. This interaction is a dispersion force. Now think about this particular instance where you have 2 adjoining helium atoms. They're part of some sort of solid. You're looking here, the electrons are on this side, the electrons are on this side. Here you have a negative side, here you have a relatively positive side, here you have a negative, here you have a positive. These two sides have no interaction at all because you have positive, positive, there's no interaction because the electron density or the charge distribution is not in a favorable manner. But in the next period of time, this thing can shift over here, and then you can end up seeing that dispersion effect, and the clumping may occur. But just because you have clumping, it doesn't mean it won't go away, because these electrons are constantly moving. So you have these periods, short periods of clumping and not clumping, and that's why these type of forces are weak. When you talk about this dipole to dipole interaction where you have a polar molecule and that molecule is comprised of atoms with different electronegativities, you can have this type of interaction arise where you can have a permanent dipole. As an example of a dipole-dipole in a polar molecule with a permanent dipole moment, consider this formaldehyde. It looks like this. You know oxygens are electronegative, they have a partial negative charge. Carbons are relatively electropositive, there's that positive charge. You have a permanent dipole in this direction, a dipole moment. Think about another formaldehyde compound, and you know it's directed in this way. You have a negative charge here, you have a positive charge here, a permanent dipole in that direction, but this can interact with that because you have a partial negative, partial positive, and you can have this good interaction between the two, a dipole-dipole. But these type of interactions are found in those molecules which have certain asymmetry, and there's a permanent dipole. You can have, however, some compounds out there where you would expect to have dipole-dipole interactions, but you may not, even though they're comprised of atoms of varying electronegativities. Here's one example, carbon dioxide. You know this is electropositive, these are electronegative, and you have a dipole moment in either direction, but the problem is they cancel each other out. You end up seeing expected polar molecule end up being non-polar because of symmetry. The charge has no sort of asymmetry, everything is symmetrical. You end up seeing the polarity lost and it becomes non-polar. Think about this, carbon tetrachloride. It's also another example where you would think it would be polar molecule, but it's non-polar because everything is symmetric. You lose that asymmetry of the charge and it becomes non-polar. Then these type of compounds here, they end up having no dipole-dipole interaction. At the best, they can just have dispersion because of the temporary dipole moments that they have. There is no permanent dipole moment in these type of compounds. We don't need to say much about hydrogen bonding other than the fact that anytime you have hydrogen bonded to oxygen, nitrogen, fluorine, you'd have very good hydrogen bonding occur, because if you have a certain compound, we'll just call it R, it has an O and then an H. you know you're going to have a partial negative here, partial positive, and then you have another H, then you have another O, and then another R, you have a partial negative, partial positive. These things can interact with each other by means of hydrogen bonding, and you can have compounds with very high melting and boiling points. Let's look at these four compounds and classify what type of intermolecular interactions or forces you would see. If you have hydrofluoric acid, you know you'll have hydrogen bonding, but you will also have everything else. These type of compounds are still polar molecules, and you'll still have dipole-dipole interactions. They'll be a permanent dipole, and they may still have a dispersion effect, and we'll just call that London force. These type of compounds which have hydrogen bonding will have all three. Hence, they're very good in terms of their high boiling points and melting points. Just because you're seeing hydrogen bonding, it doesn't mean you won't have that. It'll still have transient electron charge distributions. It'll still have permanent dipole moments, and it'll still have hydrogen bonding. Something like this, nitrogen, which looks like this, and we can just call it like that. In this type of compound, you have a non-polar because everything is symmetrically distributed. Here you're thinking you have electronegative atoms and you'll have some good type of bonding, but the only thing you'll have over here is dispersion forces. We'll just call that London because everything here is non-polar. There's charge symmetry. Everything cancels out in terms of dipoles. You don't have a permanent dipole here. You'll only have at best temporary dipole. Carbon monoxide is not a difficult one. You have a electropositive, electronegative. You'll have a permanent dipole moment in the direction of oxygen. You will for sure have dipole-dipole interactions because you'll have a permanent dipole here in the direction of oxygen, and of course you'll have dispersion forces, which are called London forces, because you'll also have temporary dipoles. As the electrons move about, you'll have these temporary fluctuations. Xenon will not have hydrogen bonding. It won't have that. At the best, it'll only have dispersion, just like how I was showing you earlier for helium. It'll just have dispersion forces, which are London forces. So you can see from all of these, hydrofluoric acid will have the highest melting point or boiling point because it has all three intermolecular interactions. Nitrogen and xenon will have the lowest, but we can still categorize those. But carbon monoxide will have the next highest melting or boiling points because it has two types of interactions. If you were to decide between these two, you would have to look, because they have the same type of intermolecular interactions, you'd have to look at which one has the higher molecular weight, and then which has a larger number of electrons, and or which has a larger size. And you know, when you're looking at that, xenon has a molecular weight of 131. Nitrogen will have, in terms of both of these, this will be higher and this will be lower in terms of melting and boiling point, simply because the molecular weight of this is much higher than nitrogen N2. So you can always end up classifying, this will be number 1, this will be number 2, this will be number 3, this will be number 4. We'll end the video with this question over here: which of these have what type of forces, and which one will be the highest to the lowest in terms of boiling points? When you're looking at NCl3, it would look something like this, and you'll have asymmetry of charge. You know, this is a electronegative. These are relatively less electronegative, but everything here is electronegative. You have a polar molecule here, and everything is directed in terms of a permanent dipole upwards. Here you're going to see a dipole-dipole interaction because there's a permanent dipole. You'll also see the London forces, which are your dispersion forces, because you do have temporary dipoles based on electron changes. When you're looking at this SiH force, you have something which looks like this. It's going to be a non-polar molecule simply because everything is evenly distributed. It's non-polar. There's no permanent dipole. At best, you have temporary dipoles. It'll be this first category, London forces. Remember, dispersion and London are synonymous in terms of their names. What about NH3? NH3, you know, you're seeing a nitrogen and you're seeing hydrogens. That clues you in towards hydrogen bonding. It looks something like this. Right here, you have a hydrogen bonding effect. Another ammonia molecule can easily hydrogen bond. You have hydrogen here, nitrogen, hydrogen, hydrogen. This thing can combine with that. You have hydrogen bonding over here for sure. You'll have all three because you have permanent dipole. The dipole is aimed towards nitrogen. You have dipole-dipole interactions, and you have London forces, which are your dispersion forces. Ethane. What about ethane? You have atoms here of different electronegativities, but there's not much difference between carbon and hydrogen. Ethane looks something like this, and it ends up being a very symmetric molecule with no permanent dipole moments. You don't have any hydrogen bonding, you don't have dipole-dipole interactions. At best, you have London forces or your dispersion forces. So now what remains is we have to categorize these from the highest to the lowest in terms of boiling points. In terms of boiling points, this is number 1 because you have all three. Then this right here would be number 2 because you have two types of intermolecular interactions, and these will be in the last. But which one will be higher? Then you look at their molecular weights. The one with the higher molecular weight will have the higher dispersion force. You'd have to find their molecular weights. What would be the molecular weight of this? You'd have 32. What would be the molecular weight of this? You have 12 plus 12 is 24 plus 6 is 30. Then that tells you that this right here would be number 3 and this right here would be number 4. Ammonia will be the highest in terms of boiling point, then nitrogen trichloride, then silicon tetrahydride, and finally ethane would be the lowest in terms of the boiling points. And that brings us to the end of this video. Thank you.